Hi guys, this is lesson 5.1. Okay, so it is called Max and Min Application. So the idea of this section is that they're going to give you more real-world scenarios of finding maximum and minimums. Okay, so for the procedures here, you're going to basically come up with the equations, identify your variables, and then you always want to isolate the max or min that you're trying to find. Make sure that you rewrite the equation with only one variable on both sides, and then you basically can derive it to find the critical values and then the number line. Okay, so the domain becomes somewhat critical, but not incredibly critical with these great real-world scenarios. So you'll just kind of have to see how this plays out. Okay, so for example 1, we have this box with no lid. And it has 48 centimeters of material. So if the box must have a square base, okay, and that's important information, square, find the dimensions that produce a maximum volume. Okay, so the first thing that we want to do is we're going to come up with the equation that has to do with the material. Okay, so the material is basically, let's just say we have this base and this base, and those two lengths would be the same because it's a square, and then we have this height. Okay, so if we're talking about the surface area of this box, we basically have 4 sides that are a base times height, and then one side that is a base times base. So the surface area for this is 4 times BH plus a B squared. Okay, and since we know that there's 48 centimeters of material, that's going to be the amount of surface area that we have. Okay, then the second part is we're going to come up with the second equation to maximize volume. Okay, so the volume of this particular shape would be base times height. So I'm going to say that's base squared times height. Okay, so now what we want to do is, since we're asking to maximize the volume, we're going to be using this volume equation, but we're going to use the second equation to rewrite it in terms of one single variable. So it doesn't matter which of the two variables I choose. I'm going to choose the easier one to solve for, which is going to be the h. So on the surface area formula, I'm going to isolate the h. So I'm going to start by subtracting the b squared. And then to isolate that h, I'm going to divide by 4b. Okay, so h is going to equal 48 minus b squared over 4b. And to make that look a little nicer, I'm just going to divide the 48 by 4b, and well, actually I'll just leave it as is and I'll just plug this straight in and I'll simplify the volume one. So I'm going to do a substitution method here, so I'm going to substitute that into the h. So I'm going to b squared times 48 minus b squared over 4b. Okay, so to simplify this, because the next step is going to be to derive this, I have a b squared that's being divided by a b, so one of these is going to cancel. Okay, and so at this point I'm going to distribute the b through and also divide by 4 on both of these terms. So 48 divided by 4. So 48 divided by 4 is 12, so we get 12b on the first term. And then on the second term, I'm going to multiply by b, so I have minus b cubed over 4. So really you could just call that 1/4 b to the 4th, which will be easier to derive. So let's do that. So if we derive this, okay, which is the whole point of finding a maximum, okay, so that's how you're going to find your max. That derivative is 12, and then 1/4 times 4 is 1, so we're going to get negative 1b to the 3rd. So, oh, hold on, I made a mistake back here. this should have been, excuse me, because if we have b times b squared, that's b cubed. So cubed. So this should be, let's see, 1/3 times 3 makes 3/4 b squared. There we go. Okay, so now to find the critical values, I'm going to set this equal to 0. Okay, so this is going to be 12 minus 3/4 b squared. So to solve that, I'm just going to add this to the other side. So I have a positive b squared term. To get rid of the 3/4, I'm going to divide by it, which is the same as multiplying by its reciprocal. So I'm going to multiply by 4/3. 12 times 4/3, 12 divided by 3 is 4, 4 times 4 is 16, and the square root of 16 is 4. Okay, so we would technically have a plus or minus 4 here, but if we think about the domain of our possible lengths, we should realize that both of them have to be a positive value. And we could also, yeah, that should be good enough. Yeah. So you can't have a negative length, so that makes sense in that respect. So if we do our number line with a 4 here, with our first derivative, so if I plug in a smaller number than 4, such as 0, that would give me 12, which is a positive number. And if I plug in a bigger number, like 5, let's see, that would be 25. So that would still be bigger than 12, so let's see, that would be a negative value there. Okay, so we see this uptrend, downtrend, so that's going to be a maximum when it hits 4. So if the b value is 4, then we can plug that into the h. And you would end up getting an h value of 2. So we basically have a 4, and the base is the 2 bases, so it's like 4, and what's our length? Centimeters. 4 centimeters by 4 centimeters by 2 centimeters. Okay, so it also does ask you to answer this. It's not on this particular thing, but it says answer as with a complete sentence. Okay, so I would say the complete sentence would be, so again, it's asking us to maximize the volume of this box. To maximize the volume of a box with a surface area of 48, the dimensions, whoops, would be 4 centimeters by 4 centimeters by 2 centimeters. This should be centimeters. Okay. All right, so the next question is, we have the product of two positive numbers. So the two positive numbers, obviously, if I say x and y, have to be greater than 0. Their product, which means we multiply, is 288. And we're going to find two numbers so that the sum, so I'm going to say the sum, is twice the first plus the second. And we want this to be as small as possible, so we're finding a minimum. Okay, so we're using the sum formula to find our minimum value. So I'm going to first isolate one of my variables. Let's go ahead and divide by x, and we'll isolate the y here. So 288x. I'm going to plug that into my sum formula. Okay, I'm going to rewrite this for deriving. So I'm going to say 288x to the negative 1. So now I'm going to derive that. So that would be 2 minus 288x to the negative 2. So then I set that equal to 0. And at this point I'm now solving that. So I'm going to add the 288 over x squared. I'm going to multiply by x squared, divide by 2, and 288 divided by 2 is 144, and square root. So I'm only going to use the positive value because we stated we only want positive numbers. Okay, I can do a number line to verify that this does in fact give me a minimum. So if I plugged in, let's say 0 off my first derivative, well, it can't be 0. So how about if I plugged in 1, it would be 2 minus 280, which is very negative. If I plugged in 13, that would be adding a number, so that would be positive. So you can see that this is in fact a minimum. So if my x value is 12, then I can plug this into here, and my corresponding y value would be 24. So again, to write that as a complete statement, I could say the smallest sum of two numbers whose twice the first plus the second and product is 288 is 12 and 24. Okay. So you're not really learning anything new in this section. You're just kind of applying it to real-world scenarios and using derivatives to find max and mins, which you could do algebraically, but today you are going to do it using calculus. So what I'd like you to do is do questions 1 through 4 by Monday or Tuesday, whichever I see you first. All right.